Welcome to this explainer. Today, we're going to unpack one of the most elegant, foundational concepts in all of space exploration. I mean, if you've ever wondered how we actually navigate the vast, invisible highways of our solar system without completely running out of gas, well, you are in exactly the right place. We're looking at the architecture of orbital efficiency, specifically a maneuver known as the Hohmann Transfer. It's an absolute masterclass in physics, mathematics, and engineering. And honestly, by the end of this explainer, you're going to look at every single satellite launch and Mars mission in a completely new light.
Consider this your official mission briefing for today. First, we'll tackle the space highway dilemma, then move into the two-burn solution. After that, we'll break down understanding delta V, look at some real-world missions, and finally wrap up with engineering efficiency. All right, let's get started.
Section 1. The Space Highway Dilemma. Why satellites can't just fly straight. Okay, let's dive into this. To really understand the solution, we first need to get a grip on the problem itself. Like, why is moving a satellite so complicated in the first place? Why can't they just fly in a straight, direct line to wherever they need to go?
Well, think about driving from Canberra to Sydney. Down here on Earth, you have a couple of really straightforward choices, right? You could take the direct highway and get there fast, or you could take a massive, long detour through Melbourne. I mean, both routes eventually get you to Sydney, but taking that huge detour uses a whole lot more fuel. Now, up in space, we face this completely counterintuitive reality. Moving a satellite from one orbit to another is not just a matter of pointing the nose of the spacecraft in the right direction and stepping on the gas. Out there, fuel is basically the most valuable and strictly limited resource on board. You literally can't just pull over to a gas station to fill up. And, let's be honest, AA wait times in orbit are terrible. So engineers are relentlessly looking for the most efficient way to change routes.
You see, space is just vastly different from driving a car. A satellite is always doing two things at the exact same time. It's moving extremely faster on the Earth while simultaneously falling toward it. Because of that, you can't just point and shoot. Changing an orbit fundamentally means changing the satellite's overall energy. If you want your spacecraft to jump up to a higher orbit, it absolutely must gain energy. And if you want it to drop to a lower orbit, it has to lose energy. The ultimate dilemma for mission controllers here is how to manage this energy exchange while burning the absolute bare minimum of their precious propellant. Section 2. The two-burn solution. Walter Hohmann's 1925 discovery. And that brings us to a beautifully simple answer to our dilemma. An answer formulated long before we ever even launched a satellite. Walter Hohmann was a German engineer who mathematically cracked the code on the most fuel-efficient journey between two circular orbits. Instead of constantly firing engines to fight against gravity, his solution relies on just two highly precise maneuvers. Imagine a satellite in a low orbit that needs to reach a higher one. Step 1. Burn 1. The engines fire, but just briefly. This sudden little burst of speed pushes the spacecraft outward, raising the opposite side of its path to create an elliptical transfer orbit. Then, Step 2. Coast. The engines completely shut off. The spacecraft just glides in total silence, using absolutely zero fuel, while gravity naturally carries it upward along this new elliptical path toward the higher orbit. Finally, Step 3. Burn 2. Just as the spacecraft hits the very highest peak of that transfer orbit, the engines fire one last time. This sharp burst bumps up the speed just enough to lock it perfectly into the new, higher circular orbit. So it's just two short, intense engine burns, separated by a really long, quiet glide.
This maneuver is just profoundly elegant. The absolutely crucial takeaway here is that it's the most fuel-efficient journey possible between two orbits, simply because most of the transit requires no propulsion whatsoever. The spacecraft is just following a natural path dictated by physics. Instead of forcing the ship along some inefficient direct path and constantly fighting the Earth's pull, the spacecraft is working with gravity.
Section 3. Understanding delta V, the currency of spaceflight. Now, you might be wondering, how do we actually measure this efficiency? Well, we use a currency that is essentially the lifeblood of mission planners everywhere.
This critical currency is called delta V, represented by the Greek letter delta and a lowercase v. It's without a doubt one of the most important concepts in all of astronautics. Now, it is super vital to understand that delta V is not the absolute speed the spacecraft is traveling through the void of space. Actually, it is the change in velocity that is produced by the spacecraft's engines. And because fuel consumption is directly tied to this change in velocity, mission designers treat delta V exactly like a strict financial budget. Think of it like a bank account. Every single maneuver you make in space costs a specific amount of delta V, and once your budget is spent, that's it. Your mission is effectively over.
The energetic contrast here is just staggering. To even get off the ground, launching a rocket from Earth and pushing it into orbit requires a massive delta-v expenditure of about 9 to 10 kilometers per second. It's this enormous energetic cost just to escape the thickest, heaviest part of gravity. But once you're actually up there, doing a Hohmann transfer between two nearby Earth orbits, like jumping from 400 kilometers up to 800 kilometers, that might require a delta-v of only a few hundred meters per second. By using the Hohmann transfer, you are literally spending pennies on the dollar compared to fighting gravity on a less efficient path.
Let's try to ground this in a really practical scenario with this number, 20. Imagine you're on a team designing an Earth observation satellite. You're parked down at a 500-kilometer orbit, but your science mission demands you move to a 600-kilometer sun-synchronous orbit. The catch? You only have exactly 20 kilograms of propellant left on board. Every single drop matters. If you just fired your engines continuously, you'd burn right through those 20 kilograms instantly. But by choosing the Hohmann transfer, spending a tiny bit of delta-v to create the ellipse, coasting, and then spending a tiny bit more to circularize, you preserve that fuel. And preserving that fuel means you can use it months or even years later for station keeping, which directly extends the operational lifetime of what is likely a multi-million-dollar satellite.
Section 4. Real-world space missions, from Earth observation to interplanetary travel. Let's zoom out a bit and see how this builds into the broader context of space exploration. Because the Hohmann transfer isn't just a theoretical textbook exercise. It's the very real, daily reality of spaceflight operations.
This maneuver is literally everywhere. Take geostationary communications satellites, for instance. When they launch, the rockets don't just drop them precisely where they need to be. No, they're usually placed into a temporary geostationary transfer orbit, or GTO. Then, the satellite itself performs a Hohmann-style maneuver to push all the way out to its final home high above the equator. And as we just talked about, Earth observation satellites use it constantly for orbit maintenance and little altitude tweaks. But it gets even grander than that. When we send probes to Mars, Venus, or even Jupiter, that incredible journey begins with a Hohmann transfer just on a massive, massive scale, orbiting around the Sun instead of the Earth.
Let's actually look a little closer at a Mars mission. Earth and Mars are orbiting the Sun at totally different speeds and different distances. You definitely can't just point a rocket straight at Mars and fire. By the time you actually got out there, Mars would have moved. Instead, the spacecraft enters a giant elliptical orbit around the Sun. This ellipse is perfectly, painstakingly calculated so that it touches Earth's orbit at the starting end and intersects Mars's orbit at the far end. But the timing has to be absolutely flawless. You have to launch so that Mars arrives at that exact intersection point on the ellipse at the exact same moment your spacecraft does. This intricate cosmic timing is exactly why missions to Mars can only launch during very specific windows that open up roughly every 26 months. It's all completely dictated by the geometry of the Hohmann transfer.
Section 5. The engineering of efficiency, balancing time, fuel, and gravity. Now we arrive at the tricky reality of mission control. While the Hohmann transfer is an incredibly elegant tool, engineering is always about balancing complex trade-offs between time, fuel, and gravity. Look, the Hohmann transfer is usually the most fuel-efficient way to go, but it is certainly not always the fastest. If you need a probe to get somewhere in a huge hurry, engineers might actually opt for a faster direct transfer, accepting the penalty of much higher fuel consumption. Alternatively, modern spacecraft sometimes use ion engines. This is low-thrust, continuous propulsion, which constantly burn for months on end, offering a totally different kind of efficiency. For voyages out to the deep, outer solar system, engineers use gravity assists, swinging past giant planets to steal a little bit of their orbital momentum. And in some highly specific, kind of weird orbital scenarios, a 3-burn bioelliptic transfer can actually save even more fuel, though it takes drastically longer. The point is, mission planners have a whole toolkit at their disposal, but the Hohmann transfer, that is always their most reliable wrench.
And I think this brilliantly illustrates the core philosophy of spaceflight. Good engineering is not about using more energy, it is about using energy more intelligently. Engineers don't just sit around and ask, can we get there? They ask, can we get there using the least possible amount of fuel? By allowing gravity to step in and do the lion's share of the work, we achieved this beautifully simple, optimized solution that has allowed humanity to explore our solar system for decades.
So I'm going to leave you with this final thought. Spacecraft rarely, if ever, travel in straight lines. The smartest path is almost always a carefully calculated ellipse. The next time you step outside at night and see Mars shining up there in the sky, think about the invisible mathematical architecture that's connecting our worlds. Ask yourself, when we send a rover to that little red dot, are we really flying there? Or are we simply giving it a little push and letting gravity do the heavy lifting? Thanks for joining me on this explainer today. Keep looking up.